Hello chemistry students and chemistry enthusiasts. In this video, I'm going to be going over how to name simple substances, simple compounds. We're going to start off with binary covalent compounds. We'll move on to binary ionic compounds, both with representative and transition metals as their cations. We'll move on to ternary ionic compounds, and finally, acids. Now, though the rules may seem obscure or arcane, or you don't really understand why they're there, but the idea, the overarching idea in names for chemicals in chemistry is that you want to have the shortest name, but that gives you a complete set of information about how many atoms of each element are in that substance and how that substance is put together. So this will be the IUPAC naming of system compounds. IUPAC is the International Union of Pure and Applied Chemistry. It's really like the official chemistry organization that decides on these rules. We're going to start off with naming for the simplest things, which would be binary covalent compounds or binary molecules. So they do not have a charge overall. They are held together with covalent bonds. They're made of only non-metal elements, and there are only two elements. That's what binary means. Now, covalent compounds or molecules, when they have more than one element, they might combine in different ratios. And so it's important to have a way to say how many atoms of each element are in that molecule. And the prefixes indicate how many atoms, and the prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca, etc., meaning 1 through 12 respectively. So you use the prefix mono to indicate that there's one atom of that element, except if it's the first element in the formula, you would not include the mono. And whenever it's oxide for the second element, you would drop the O on mono or the A in penta or tetra. Notice too that the second element has the beginning of its name, but then it ends in IDE. Next will be binary ionic compounds. So that means binary, that it's a compound with just two elements. And they're ionic compounds, and so they're not molecules, but they are formula units, and it's a metal paired with a non-metal. And recall that the metal is going to be the positive ion, called the cation, and the nonmetal is the negative ion, the anion. Now, a formula for a binary ionic compound needs to be balanced by the charge on the ions. So whatever the charge is on the metal has to be balanced out by the charge on the nonmetal atoms. It's for this reason that the ratio is implied and there should be no prefixes used on these. The prefixes will be extra information because you're meant to use the charge to understand and know how many of each element would be present. Having a reference for trends for ionic charge can help you. You can see which things have negative charges in these columns, and you can see what things would have positive charges and what their positive charge would be. So for example, when magnesium pairs with chlorine, magnesium has a 2+ charge, and to balance out charge for a neutral compound, there would have to be 2 chlorines because each chlorine is a 1-. And so just saying magnesium chloride, if someone knows their trends for ionic charge, they would be able to know that the formula is MgCl2, and therefore saying magnesium dichloride would be redundant and extra information. So again, you're going with the shortest name that still provides enough information for someone to correctly write the formula. Again, the name magnesium dichloride would be incorrect in this case. It is simply magnesium chloride because it's an ionic compound, and ionic compounds are balanced by charge, and so the ratio of each element is implied by looking at the charge. Now, when you look at this reference, the trend for ionic charge, there are a lot of metals that are in this area of the periodic table that are not shown. It doesn't show their trend for ionic charge. And here, things like lead and tin and iron and copper and manganese, they're not on here. And that's because that those metals are transition or post-transition metals, which could have different charges depending on the situation. And because some of these metals that are in this shaded area, those transition and post-transition metals, because they can have multiple charges, their charge needs to be stated when you write out their name, and that's using a Roman numeral. These metals that are here that have a predictable charge, those are called representative metals, and they would not need a Roman numeral to indicate their charge. That would be extra information. But any metal that is in this shaded area needs to have a Roman numeral after its name when written down to indicate its charge. We'll look at 2 examples next. So I've got 2 examples here. Fe is iron, and we've got iron and chlorine. Just saying iron chloride would not be a good option for this because iron is a transition metal. It could have different charges, and so you need a Roman numeral after writing the word iron to indicate the charge on this. Now we can try to figure out what the charge on this is because we look at what the other half of the compound is. And we see that chlorine does have predictable charge of -1, and that there are 3 chlorines, all of which would have a charge of -1. And because of this, and we know that ionic compounds, their charges are balanced out, so with 3 -1 charges and a single iron atom, that single iron atom has a 3+ charge, and so its name would be iron with a Roman numeral 3 and then chloride. In this case, we look to the oxygen, what its charge is, knowing that the iron would have to have a opposite charge. So with oxygen having a 2- charge, the iron in this case, to balance it out, would have to have a 2+ charge. We'll look at one last example with iron, Fe2O3. It works the same way, the same process as the others, where you look at what you do know the charge of, which is oxygen, or oxide, has a 2- charge. And we can see that there are 3 oxygens, each one with a 2- charge. So if 3 oxygens, each one with a 2- charge, are present, we know that there's a total of 6- for a charge. To balance that, we know that the irons together would have a 6+ charge, but the Roman numeral should be for a single iron atom. Visually, we can represent this compound like this, that there are 3 oxygens, and we know the charge on oxygen is 2-. We're looking for what the charge is on a single iron, and so we can see that while both irons together have to have a +6 charge, each one would have +3. And so the name of this would be iron 3 oxide. Next, we'll move to ternary ionic compounds. And these are ionic compounds where that means something has gained electrons and something has lost electrons. And there's at least one thing called a polyatomic ion. A polyatomic ion we've talked about previously is that it's a group of covalently bonded atoms, kind of like a molecule, that are sharing electrons between them, but it has an overall charge. So to become stable, it has either lost or gained electrons. They're almost all negatively charged, the ones that you would come into contact with in a course like this. The one positive polyatomic ion that you would come in contact with in this course would be ammonium, NH4. Otherwise, it's going to be a metal paired with a negatively charged polyatomic ion. We have references for common polyatomic ions that you would encounter in a high school chemistry course. The reason for this is that there are 2 ways that people might write acetate. They mean the same thing. So notice that there are 2 carbons, that there are 2 oxygens and 3 hydrogens in this first formula, which is just condensed here. You'll get a copy of this handout for reference, and it tells the charge. If there's no number, it's implied to be a 1- or a 1+. The subscript, remember, is different from the number on the charge. So this is BrO2, that means 2 oxygens, and it has a 1- charge. Or here, NO3 has a 1- charge, and it's called nitrate. And so notice that most of these have ate or ite endings. And so when these are in compounds, you would keep those ate or ite endings. You wouldn't change it to ide, like changing chlorine to chloride when it's in a binary compound. That's how you can tell if it's a ternary ionic compound typically, is if the ionic compound ends in ide or ate or ite. Ate or ite would typically mean that it's ternary, that there's a polyatomic ion. So for an example, we'll look at sodium oxalate, how to find its formula. We would look for the charge on sodium. Since it doesn't have a Roman numeral after it, we know that it's going to be one of the ones that we should be able to find on here. So sodium is here and it has a 1+ charge. Oxalate So because it has an ATE ending, we know it's going to be one of our polyatomic ions, and we can find it here, C2O4 with a 2- charge. Now it's the same naming rules and formula rules as other ionic compounds, and so the charges need to balance. So we need to think about how many oxalates would we need and how many sodiums would we need so that their charges balance. We can see that we would need 2 sodium atoms to balance out the charge from the 1 oxalate, since it has a 2-. And so its formula would be this, indicating that there are 2 sodiums, each with a 1+ charge, and 1 oxalate. Again, there's no Roman numeral after magnesium because it's a representative metal, and so we can look up its charge, that it has a 2+ charge. Cyanide is one of the polyatomic ions on your list, and you can see it's a Cn with a 1- charge. And we can see from these that since the charges don't balance, we'll need to have multiples, that for every 1 magnesium, which has a 2+ charge, that you would have to have 2 cyanide ions. And if we wanted to put that there are 2 of these, we would need to put the entire polyatomic ion, since it's 2 atoms, in parentheses and put the 2 afterward. Like this. Look at an example with a transition metal. So in this case, we would look up that copper is what Cu is, and we need to check to see if copper is a metal that needs Roman numerals or not. If it's not listed for its charge when you find it on the periodic table, like copper is right here next to zinc and above silver, you know that it is going to need Roman numerals if it's in any of these shaded areas. So I'm going to put parentheses in the name to leave it for the Roman numeral once we figure it out. NO3, we can find that is on our list of polyatomic ions. Its name is nitrate, and it has a 1- charge. Now we can use the fact that this has a 1- charge to figure out what the charge on the copper is, since it needs to balance out. The nitrate has a 1- charge, but there are 2 of them indicated here, and so the copper has to be 2+. We'll look at one last example where we go from a name of a transition metal ionic compound to its formula. Iron 3 chlorite, we know that iron is Fe. Chlorite, we can find it on our list of polyatomic ions. It's ClO2 with a 1- charge. The question is, for these charges, how many of each would we need? The 3 here tells us that the iron has a 3+ charge. Chlorite, from our list, said it was ClO2 with a 1- charge. And so we can see that these 2 do not balance each other out based on charge, that we would need 3 of these represented. And to represent that in a formula, we would put the ClO2 in parentheses and a 3 afterward. Last, we'll look at how to name acids. Acids are a special type of covalent compound or molecule that when you put them into water, they release their hydrogens. Their formulae, if you're looking at a chemical formula, they typically start with hydrogen. And so you'll know if you have an acid if its formula starts with that. Acids have 2 ways of naming them, whether they are binary or ternary. If it's a binary acid, binary means 2 elements, and so it's hydrogen as one of the elements plus one other thing. Those are the acids whose names start with hydro, and so you would say hydro, and then the base of the other element, and then the ending ic acid. For example, HCl is a binary acid, and it's hydrochloric acid. Most acids, however, are ternary, where it's hydrogen or multiple hydrogens with a polyatomic ion. Now, to figure out how many hydrogens would pair with that polyatomic ion, you look at their charge. So for instance, if there's an acid that's based on hydrogens with this polyatomic ion, the 2- charge means that there need to be 2 hydrogens to start off. And so an acid that is based off of this carbonate ion would be H2CO3 because of the 2- charge. Or an acid based off of this ion, since it has a 1- charge, it would just be HCN. The rule about naming ternary acids is that they don't start with hydro. It's just the root of the polyatomic ion, and then if the polyatomic ion ended with 8, then it changes to ic and then acid. If it ended in ite, it changes to OUS and then acid. And so, for example, HNO2, you ignore the H and you look for what polyatomic ion that was, NO2, nitrite. And because it ended in ITE, it would be OUS. So this would be nitrous acid. NO3, so you give up the H, the NO3 ion was nitrate, and so this would be nitric acid. We can do the opposite. We'll look at a name and write its formula. So the OUS ending on this means that it had an ending of ite, so we're looking for sulfite. Sulfite, we can see, is SO3 with a 2- charge. That 2- charge means that there would be 2 hydrogens paired with this ion in its acid formula. So I hope that was all clear enough. We'll be looking at some examples in class, and after watching this, you should be able to, when just picking a substance at random, its formula, be able to tell what type of those 4 it is, whether it's a binary covalent, whether it's a binary ionic with a representative or transition metal, whether it's a ternary ionic, or whether it's an acid.